wire capacitance. So we have a capacitance also between the wires. So we have a wire, for example, here at the core we have the wire at the top and bottom, and also we have a neighboring wire left and right, right? All these things contribute the capacitance, right? So total capacitance will be C top, C bottom, and 2 C adjacent capacitance, right? So this core metal sees this much capacitance. So when you draw the metal, try to make if you want to draw the signal line, try to minimize the coupling, this kind of all these coupling capacitance. We want to minimize there. The worst case happen when you are running the signal in parallel, then you will see a lot more area facing. It gives us like a larger capacitance. So trying to minimize the capacitance, to try to metal, rather than running in parallel, you like a cross section, it like a metal signal crosses, so that the cross section, I mean neighboring area facing the area facing each metal is minimized, which means smaller capacitance. The capacitance trend, we will see how the capacitance vary over the process generations. So we know that if there is a parallel two plates, the area is dA and distance is d, then the capacitance between two plates will be epsilon times area over distance, right? So we know that increasing the wire area, let's say for example if I have two parallel plates here, if the wire width is smaller, narrower, then we get the lower area, but at the same time we also have the shorter distance, the d, as we scale down. So it is not quite sure whether the capacitance will increase or decrease over the process generation. But what we can see is that for the finer process, we know the metal structure looks like this kind of dimension, right? So the side area, rather than width, the thickness kind of very thick. So if we have two lines running in parallel here, the capacitance between them will be greater than the capacitance between the metal layers, right? Because it has more area in case if we have a parallel wires there. So we have to avoid that kind of a parallel wire, or we have to make it separate apart enough so that to minimize this kind of the sidewall capacitance. The sidewall. So the capacitance also determined by the dielectric constant. The dielectric constant is K times epsilon 0. Epsilon 0 is from the air. For the silicon dioxide, K equal to 3.9. So for low K dielectrics will kind of lead to smaller capacitance. for this is the process requirement. So typically K is similar to 3 because we use the dielectric uses the air pocket or something like that. So that is kind of similar to that. In sometimes we use high K gate dielectric because if you use the low K dielectric, then it increases leakage current. So high K has a better control of a channel charge on the gate with a high electrical field below there. So when we use the high K the material, then we to reduce the capacitance we use the thickness distance between poly and channel, like make it thicker. So this is for the gate dielectric trained. This is something different from the wire we had learned there. So this is for especially for the MOS device trend. So we have a leakage from the gate, and the channel, the current will leak out some of the current there. So we want to minimize that. Typical wires have 0.2 femtofarad per micron. So compare to 2 femtofarad per micron for gate capacitance. So for example, if I have like a 1 micron device, it will have a 2 femtofarad for minimum channel length L mean. This is a 2 femtofarad gate capacitance, and typically we place the contact and metal, draw the metal, right? So for the same length of the metal, for example, 1 micron, that gives us a 0.2 femtofarad, right? This is something that you can have in your mind for estimating your layout parasitic. So when we route the signal with the metal, there's also someone may consider diffusion and polysilicon as a routing wires. But when you see like this structure, let's say M plus MP sub, we have a diffusion here. This one has a very high capacitance out of this parasitic diode. So this is quite comparable, meaning similar to gate capacitance. This capacitance is very similar to that of the gate capacitance. Also, it has high resistance. It doesn't have a low resistance like a metal. So for long distance, we should avoid using this diffusion for signal routing. The polysilicon itself, the polysilicon here, you may use that for signal routing. It has a lower C than the diffusion capacitance, but it also has high resistance from the poly line. So this is only for use for gate, transistor gate, and sometimes we use this poly as a routing for very short wire connection between the gates. For example, if we have two transistors there, between them we connect them together for sharing this contact, the M1, something like that, sharing the poly. We can use this kind of a limited usage. So but you cannot make this like a long long connection like that, because it has a very high resistance. We have to avoid that. Also, it also have a large capacitance also. So wire itself is a distributed system. Consider that we have a line running. So each section will have a resistance and also capacitance to the substrate. So this is kind of distributed system. So we model that wire with the distributed like an N segment wire, so resistance and capacitance. This is quite complicated for hand analysis. So we simplify this distributed model using L model, or the first one is L model, second one is pi model, third one is T model. So mostly the L model for RLC, we lump that all the C on the right hand side, but pi model we split those capacitance left to the left and right. For the T model we center that the capacitance in the middle of the resistance. So typically 3-segment pi model. So we use 3 segment, meaning we have a 3, let's say RLC 2 1 2 3 R over 3 R over 3 R over 3, and capacitance is what 1 2 3 4 5 6. So 6 C over 6 each one. We can have a 3 pi section there. So this is accurate for the delay simulation. It is almost accurate within the accuracy of 3% in simulation. So when you launch the signal there, you see the output at the right hand side. The delay measurement is quite accurate using this pi model, 3-segment pi model versus a distributed model. For the same accuracy, when you use the L model, it requires 100 segments. So we better use pi model. So pi model is quite widely used for calculating the Elmo delay. You know that how to calculate the delay from the X to Y here, input Y, using the Elmo. We have learned that before, right? So we can pretty accurately estimate the delay out of the line resistance and capacitance. Let's see the example. Let's consider metal 2 wire in 180 nanometer process. So it has a 0.32 micron wide and length is 5 millimeter long, right? Quite large line, long line there. Let's estimate the RC first. So to calculate the resistance and capacitance, we need to know the R square. So once we know the R square, we can count how many squares there, right? So 5 millimeter over 0.32 micrometer will give us a number of squares that give us a total resistance by multiplying R square equal to R equivalent, right? For C per micron is that, so if we know that per micron for the minimum channel length, this width, so per micron capacitance, if we know that per micron capacitance, we can calculate the total capacitance there, right? For example, so let's say R square is 50 milliohm per square. Then we can calculate the total resistance, how many squares we had. from previous example, using that result, we can calculate the total resistance. And also, C per micron is 0.2 femtofarad. That leaves us a total 1 picofarad. Once we know this, we can use the 3-segment wire model, pi model, 1, 2, 3. So this is R over 3, and this is just 6 over C, right? Each section will have R and C out of the pi model there. Once we know this pi model, then we can do some delay analysis using the Elmo delay calculation. Let's say if we launch a signal there, how it will come out with some delay. So how much delay we get? This is from the Elmo delay we can consider. This is an example of calculating wire delay. Let's assume that we're trying to estimate the delay of the 10x inverter driving wires, and then through we have a 2x inverter at the output. So from here to the output, from x to y, how much delay we'll get. So this wire length is the 5 millimeter. So first, we have to estimate how much driving resistance is and how much load capacitance is, right? CL. And drive, if for example for pull down case, let's say inverter, pull down inverter will seize the resistance. This one will have some resistance. This is 10x. So unit inverter has a 0.36 micron NMOS and 0.72 micron PMOS there. So 10x means 3.6 micron NMOS versus 7.2 micron PMOS, right? So P and something like that. So how we estimate? So for the given resistance 2.5 kilo ohm per micron, so we can calculate the RGRV, inverter R inf equal to what? 2.5 kilo ohm per micron divided by 3.6 micrometer. That will give us some number, right? And also the wire resistance information should be there, right? And capacitance as well. So, and also input capacitance. For example, here input capacitance is 4 femtofarad out of the inverter, 2x inverter. This is the 1x, this is the 10x inverter driving resistance. So this is the wire resistance. Let's say let's assume that we have a 5 millimeter wire has like this kind of pi model there. Then when we calculate the delay, we'll get the Elmo delay. So first, 500 femtofarad times resistance going up to there is 690 plus another 500 femtofarad. How many resistance in the path? We have a 690 plus a 781, right? Oh, and also we have to lump those two, 500 and 4 femtofarad. So 500 4 femtofarad, 500 4 femtofarad. So if you calculate this number, then you will got the 1.1 nanosecond.